So the next part of data link layer, the next important concept are called multiple access protocols. Sometimes these are also called as media access protocols, right? So again, we've discussed about this briefly when we introduced about what the data link layer is all about. So in short, your multiple access control or media access control protocols or media access protocols are basically imagine if I have a medium here to which all my hosts are connected. Again, when we study multiple access protocols and media access protocols, we sometimes use this term called stations instead of hosts, because most of the terminology, most of the concepts or protocols that we learn about were actually developed by communications engineers. Okay, for communications engineers, it need not be a computer. It could be anything. It could be a radio, right? It could be a satellite. It could be anything, right? So that's why they use the term stations instead of hosts. So in your textbook or on Wikipedia, if you see that term station, that is nothing but hosts in the context of computer networks. Because many of the concepts that we will learn of in this video were actually designed by communications engineers, right? Again, this is even prior to computer networks even came into existence, right? So suppose imagine if I have a bus architecture. Imagine if I have a bus architecture or a bus topology onto which I have multiple hosts or stations that are connected. Now look at this. All of them have to use the same medium or the same wiring here. Like this is a guided medium. Imagine instead of a guided medium, I have unguided medium like wireless communication, right? All of them use the same air to transmit their signals in. So in such a case, the medium is being accessed by all the hosts or stations. Now, how do they access? How do each of these hosts or stations access the medium without any collisions? Again, remember, when do collisions happen? Imagine if host 1 sends a packet or a frame. At the same time, let's assume host 2 also sends a packet or frame on the same wire, right? These two, at the end of the day, these are electrical signals or these are light signals or electromagnetic signals, right? If they both overlap, they will interfere, they will collide, and it will create useless data. Now, we don't want them to collide on this wire. We don't want them to coexist at the same place in the wire at any same time, because then they collide and there will be literally the final data that you get after they collide is completely corrupted, right? So media access protocols or multiple access protocols, their job is to ensure that these hosts are accessing the common medium they have, whether it's a bus or whether it is air when they're using wireless communication, such that all of them are accessing in such a way that we don't have collisions. That's the core concept here. And your multiple access or media access protocols broadly are divided into 3 categories. The first one is called channelization protocols, where we take the channel or the medium, and use either frequency or time or code division. Again, I'll describe these things in detail. There are 3 channelization protocols which are very often used. Some of you may have encountered CDMA. There are some telephone providers today, there are some telecommunications providers in some parts of the world who use CDMA instead of GSM. You may have heard of these terms, GSM phone versus a CDMA phone, right? Or your telephone carrier, or your telecommunication provider is a CDMA provider or a GSM provider. That's the same CDMA that we will study of briefly here. Again, this is studied in much more detail by electronics and communications engineer. In the context of computer networks, we'll briefly touch upon these concepts. We'll not go too deep into the deep mathematical concepts of how they work. That is something that the electronics engineers study in a lot more detail, right? So the second thing is called controlled access protocols. The third type is called as random access protocols. Again, within controlled access protocols, there are multiple protocols that we will study of. Even in random access protocols, we'll study multiple protocols. So the rest of this chapter in the context of multiple access protocols and media access protocols, I'll just call them as MAP for short, right? We will be studying most of these protocols in some depth. Some of them we'll study in a lot more detail. Some of them which are much more relevant in the context of computer networks we'll study in a lot more detail. Some of the protocols like CDMA, we'll just touch upon it just to get an idea, because to study them more, you will have to study communications engineering. right? So we'll touch upon some of these ideas. So first, let's start with channelization protocols. We'll start with FDMA, TDMA, and CDMA. In the next few videos, we'll study the rest of the protocols. Okay, the first channelization protocol that we will study is called FDMA. FDMA basically means frequency division multiple access. Sometimes people instead of using this FDMA, they just say FDM. What they mean here is frequency division multiplexing. Again, it's a very simple concept. Okay, let's assume. I'll take a simple example so that you'll understand it. Imagine I have wireless medium. Imagine I have multiple hosts or stations. Imagine I have 9 stations or 9 hosts. They all are connected via wireless, right? They all are using the electromagnetic signals, right? The wireless signals, radio signals basically. Let's assume we have the range of frequencies. This is the range of frequencies which I can use to transmit data from any host to any host, right? Let's assume I can use from 100 megahertz to 1000 megahertz. What is again, we have talked about frequencies when we studied about computer organization, right? So what is 100 megahertz? 100 million cycles per second. That's my clock speed at which I'm transmitting my, that's a clock speed which I use for all of my encodings. When I have 1000 megahertz, that means the clock speed that I have, my clock which I use for encoding. We have discussed about encodings, right? Manchester encoding and differential Manchester encoding, etc. There we use the clock. If the clock runs at 1000 million hertz or roughly 1 gigahertz, or if the clock moves in these many cycles per second, right? That's what is frequency literally. This is the frequency of the clock literally, which is used for the actual encoding of the signals. Now in frequency division, look at the name. What does it say? Frequency division, right? Multiple access. It's a very simple concept. What it says here is, it says I have 9 hosts here. So let's break down this whole frequency into 9 non-overlapping frequency intervals. So I could say from 100 megahertz to 199 megahertz, I will allocate it to H1, host 1, which means host 1 will always transmit signals only in the range of 100 to 199 megahertz, right? That's the only range in which it will transmit signals out. My host 2 will only transmit signals in the 200 to 299 megahertz. So there is a distinct, see, look at this. I'm taking the whole frequency. I'm dividing this frequency into 9 distinct non-overlapping parts. So 100 to 199 for this, 200 to 299 megahertz for this, 300 to 399, so on and so forth, 900 to 999 megahertz for this. Now what happens whenever it sends a signal, it will send at a completely different frequency than the signal that it sends. Which means because they are all, look at this, my whole frequency is divided into equal sized. In this case, we are dividing it into equal sized windows or equal sized bins or equal sized range of frequencies, right? Now what happens? Because this is transmitting at a completely different frequency, this is transmitting at a completely different frequency, there is no way they'll get jumbled up, right? So this is called as a channelization strategy because we are taking the properties of the channel. What is a channel property? Through my channel or through my medium, which is air in the case of wireless medium, right? My whole channel, which is literally radio waves that I'm using through my medium or channel called air, this is the range of frequencies I can send. So I'm basically taking this whole thing, I'm taking the channel, I'm breaking the channel through some specific means wherein I'm breaking it using frequency ranges here. That's what FDMA or FD, frequency division multiplexing, is all about. Very, very simple concept, right? Very simple concept. Now the second strategy is called time division multiple access. This is also a channelization strategy. This is also called time division multiplexing sometimes. This is your TDMA. Look at it, just to give you the context, where are we? We are studying we have seen FDMA, we'll study TDMA and CDMA, right? Again, some of the internal details of how FDMA works, how a signal, there are some additional details here that typically communications engineers typically study. Things like what is Shannon's entropy, lots of information theory concepts, all of that are studied by electronics and communications engineer. It is not too important in the context of computer networks per se, right? So now let's see. The next concept is called time division multiple access. It's called TDMA. So what I do now is this. Look at this. Imagine all of these hosts or stations are connected to the same medium or channel. Then what I do here is I take the whole time. This is my time axis. What I do now is I break my time axis into these intervals. So in this interval of time, I'll assign this to host 1, which means from this time to this time, if host 1 wants to send any data through my medium, it can send. It can't send. See, it's literally like allocating one interval of time. That's why it's called time division, because we are dividing the whole time into intervals. Earlier, we divided the frequency into intervals. Here, we are dividing the time into intervals, right? So I assign this much time. During this time, my host 1 or station 1 can transmit the signal it wants to transmit. Then next comes the turn of host 2, right? Then host 3, host 4. So every host gets a turn. Eventually, after the nth host gets a turn, cyclically we'll give the turn back to host 1. Look at this: host 1, host 2, host 3, host n. Then again, we'll start with host 1, host 2, host 3, host n. Right? So here, what am I doing here? I'm dividing the total time that I have into intervals, and in each interval, I'm giving it's literally like giving turns to various hosts or stations in a cyclical order. Now let's assume here that all the packets are of the same size. Let's just make a simplifying assumption. If all the packets are of the same size, then I can actually give, look at this, then each of these intervals can be of the same size. Each of these intervals can be of the same size. And what should be the size of each interval here? Because all packets are of the same size, how much time does it take to place one packet? So for example, imagine all of them are of the same packet. Let's assume I have host 4 here. Let's assume this is the turn of the host 4, which wants to place a packet or frame, right, onto the channel here. Now it takes TT time to place it, and it takes TP time to propagate it to the destination. So this whole time interval should be TT plus TP, right? The whole interval should be TT plus TP. Now imagine a world where every host has one packet or frame that it wants to send. In such a case, what will be my efficiency? How do I measure my efficiency? I measure my efficiency as the time that is used for transmitting, which is TT, by the time which is used for the total time. The total time, look at this, host 4 has spent T lowercase t, T subscript T, for transmitting my package. The total time is TT plus TP. Imagine host 1 sent a package here, host 2 sent a package here, host 3 sent a package, host 4 sent a package, host 5 sent a package. Then what is the total efficiency? Total efficiency is TT into N, because in these N time intervals, I'm sending N packets. If every host has a packet or a frame to send, right? This is the total time into N. These two N's will cancel. So my efficiency will be TT by TT plus P. And we have shown earlier in the previous videos that it is equal to 1 by 1 plus A, where A equals to TP by TT. Same math as we have shown earlier. We have shown this math earlier. And we've also shown that throughput or effective bandwidth or utilized bandwidth is nothing but efficiency into the total bandwidth. This math is exactly the stuff that we have seen earlier. Same math, nothing changes here, right? Very simple concept here. Now there is one major drawback of TDM. There is one major drawback, which is called as wasted slots. What does it mean? Imagine this slot is assigned for host 1. Host 1 has a packet, it sent a packet. Host 2 has a packet, it sent a packet. Now let's say host 3 or station 3 does not have a packet. It does not have any data packet to send. But this time is pre-allocated. This interval of time is allocated for host 3. Now if host 3 does not want to transmit any data, if it doesn't have data to be transmitted, this whole time is simply wasted. If you have more time wastage, your efficiency also will drop, right? If you have wasted slots, if there are some instances where some hosts or stations don't want to transmit data, then what happens? That time is completely wasted, right? Simply it's completely wasted. So you want, again, if you have wasted slots in your ecosystem or in your system, if you have wasted slots, your whole efficiency will decrease, right? Because there are some instances where I don't have any data to send, so my transmission time will not be there, but the total time will still be there, right? So in this case, let's assume I have 4 slots, right? So what is the efficiency here? 4. So what this is TT into 3, because in this I have placed one packet on the channel or on the medium. Here I placed one packet or one frame on the channel or medium. Here I placed one packet on the medium. Here I didn't place anything. That's why TT into 3 by, what is the total time now? Each of this is TT plus TP, right? Each of this is TT plus TP. I'm assuming here that all packets are of the same size. Then I have denominator 4, right? So what is this? This is 3 by 4th into 1 by 1 plus A. Look at this. I have this 3 by 4, right? Right? So 1 by 1 plus A was my initial efficiency. If every host or station had a packet to send, the efficiency was 1 by 1 by A, right? But in this case, what happens? There is one station which did not have any data to send. There is one wasted slot here. Of the 4 slots, 1 slot was wasted. So my efficiency has dropped to 3/4 of this. So there is actually a drop in efficiency now because there is a wasted slot here, right? So one of the drawbacks is wasted slots, which results in reduced efficiency, right? We never want our efficiency to reduce, right? So this is one of the major drawbacks. Now let's take a very simple problem and solve it. Very, very simple problem. Imagine my TT is 1 second, one TP is 1 millisecond. Okay, let's assume I'm using time division multiplexing or time division multiple access. Let's assume I'm using time division multiple access. What is my efficiency? Very simple. What is efficiency? 1 by 1 plus A. What is A? TP by TT. Right? Simple math, which is 1 by 1 plus TP and TT are the same. So 1 by 1 plus 1. I'm sorry, 1 by 1 plus 1. So my efficiency is 50% now. Why is my efficiency 50%? Because I'm spending amongst the 2 milliseconds, I'm spending 1 millisecond to place the packet on the wire or on the medium. I'm spending 1 millisecond for it to be propagated, which means I'm only utilizing 1 out of 2 milliseconds. That's the core idea. You don't even have to remember this formula. If you know the concept, you can arrive at this formula on the fly, right? Second, imagine if my bandwidth is 4 megabits per second. This is my bandwidth. Then what is my throughput or available bandwidth? What is it? Available bandwidth is nothing but my efficiency multiplied by B, right? We have seen this, right? Throughput is nothing but efficiency multiplied by my bandwidth. We have seen this in the previous videos also. Very simple. So now it's 50% multiplied by 4 Mbps. So it is 2 megabits per second. This is my effective bandwidth or available bandwidth or my throughput. Now if every station or host needs an effective bandwidth or a throughput of 1 kilobits per second, imagine this is what it wants. Then the number of stations that I can connect here. How many stations can I connect now? Remember, each station wants to have an effective bandwidth of 1 kilobits per second. What is my effective bandwidth now? 2 Mbps. What is 2 Mbps? 2 into 10 power 6 bits per second. Right? This is my total bandwidth. Now if I spread this bandwidth, if I break this bandwidth using time division, right? How many? So I don't know how many. The question here is number of stations that I can connect. Each station wants 1 kilobits per second effective bandwidth, right? So which means by 1 into 10 power 3 bits per second. Now what is this? This is 2000. So now I can have 2000 stations or 2000 hosts connected to this channel or to this medium, which has an actual bandwidth of 4 megabits per second and an effective bandwidth of 2 megabits per second. I can connect 2000 hosts to this. Suppose if I have a medium like this, right? I can connect 2000 hosts here. I can connect 1, 2, so on and so forth, 2000 hosts here, where the effective bandwidth of each host will be 1 kilobits per second. That's it. Very common sense. High school mathematics, right? Now let's look at channelization technique, which is CDMA. Again, there is a lot of interesting mathematics behind CDMA. Some of the concepts that we learned in group theory, if you remember, in discrete mathematics. You may have learned about group theory in discrete mathematics. We also have a course called discrete mathematics where we cover group theory, right? There are some very interesting concepts in group theory which are used in CDMA. There are also concepts in linear algebra. There are also concepts in linear algebra that are used in the design of CDMA, right? Again, these mathematical concepts and how they are used are typically studied by electronics and communication students. Let me give you a high-level overview of how CDMA works, right? Imagine I have a bus. Imagine I have bus topology. This is the medium that connects, let's say, 4 hosts. So what we do is this. Look at this. This host, let's assume, wants to send some data D1. This host wants to send data D2. This host wants to send data D3. This host wants to send data D4. What happens now is this host multiplies this data with a code. Every host has a unique code. The design of the code is what is used in group theory and linear algebra concepts, right? So this data is multiplied by this code. This data is multiplied by this code. This data is multiplied by this code. This data is multiplied by the code, and it is placed on the bus. Look at this. So all four of them. So what is actually finally placed on the bus is C1 D1 plus C2 D2 plus C3 D3 plus C4 D4. The summation, or in other words, summation of Ci Di, code multiplied by data of all the hosts, I equals to 1 to 4 in our case. This is the final value that is placed on the bus, right? And because of the way these codes are designed using concepts from group theory and linear algebra, right? Wherever this has to go, wherever this data has to go, suppose this data has to go from host 1 to host 4, right? Where, see, all this, look at this, all the data, your D1, D2, D3, D4, all of it is present simultaneously on the same medium. It is simultaneously present on the medium, right? But because of the way these codes are very smartly designed and very intelligently thought of using concepts from group theory and some very ingenious mathematics, simple but ingenious mathematics, you can decouple this data. You can from this total signal, what is carried on the bus, this is carried on the bus, or this is carried in the medium. But you can easily separate D1, D2, D3, D4 because you know what C1, C2, C3, C4 are. It's very easy to decouple or to separate out the data from the codes. And if let's assume this data has to go to H4 from H1, H4 can easily recognize, H4 will read the whole signal. Look at this, because this whole signal, summation CADI is there on the signal, H4 will read all of it, and it can do some simple computation to get D1 out, D2 out, D3 out, and D4 out, and pick D1 which is meant for H4. Okay, some very ingenious mathematics in the back end of CDMA, and CDMA is used by many mobile carriers, right? I think at some point in India, not enough, there was Reliance Telecom. There was Reliance Telecom in the 2005-2010 period, where Reliance Telecom was using CDMA. Right now, I think most other networks use GSM. There are also some CDMA networks in the US and in Europe also. Right? CDMA is very popular with telecommunications folks because using this very ingenious mathematics, they can very ingeniously send far more calls. They can actually place far more calls using the wireless medium. Very ingenious concept, right? So now we'll study other algorithms and other protocols in the next video.